So the next thing is, how do magnetic moments react when you have magnetic fields? So that is something that you can calculate, or you can decide if you have a picture. For example, if you have a loop of charge like this, and you have magnetic field lines that go like this, they diverge a bit. Let me see you use your right-hand rule and tell me whether that loop of current will feel a force up or down. Give you 30 seconds, and I take a vote. Let's see how we're doing with that. I'll prepare these blackboards in the meantime. All right, who votes up? Nobody. Who votes down? Yeah, a lot of it. Down, exactly. How do you see down? Well, one way to see it is look at the cross section. You would have this wire here, like that. The current is coming in on this side and going out this way. Here you have the field lines that go through those two edges. And the magnetic field is like that. And the force goes like I cross B. So I goes in, B goes out. The force must be like that. A little bit of force. In this one, I cross B would be like that. A little bit of force. Yep. Has a component down because the field lines are diverging. So what is the force really given by? The force is given by the gradient of mu dot B. This is derived in E&M. I will not derive it here. It's not really the point of this course. But you can see that it's consistent. This is saying that the force goes in the direction that makes mu dot B grow the fastest. Now, mu in this case is up. So mu dot B is positive because mu and the magnetic field go in the same direction. So mu dot B is positive. So the force will be towards the direction, that's what the gradient is, that this becomes bigger. So it becomes bigger here because as the field lines come together, that means stronger magnetic field, and therefore mu dot B would be larger. So it's pointing down. If you have a magnetic field that is roughly in the z direction, there will be a simplification, as we will see very soon. So what did Stern and Gerlach do? Well, they were working with silver atoms. And the silver atoms have 47 electrons, out of which 46 fill up the levels n equal 1, 2, 3, and 4. Just one lone electron, a 5s electron, the 47th electron, is a lonely electron that is out in a spherical shell. We know now with 0 orbital angular momentum is an S state. And therefore, throwing silver atoms through your apparatus was pretty much the same thing as throwing electrons. Because all these other electrons are tied up with each other. You know now one has spin up, one spin down. Nothing contributes, no angular momentum as a whole. And then you have this last electron unpaired that has a spin. So it's like throwing spins. So moreover, throwing spins, as far as we're concerned, Stern and Gerlach wouldn't care. Because of these relations, it's throwing in dipole moments. And they would care about that because magnetic fields push dipole moments up or down. Therefore, what is the apparatus these people had? It was sort of like this. Was an oven. And you produce some silver atoms that come out as a gas, a collimating slit, then you put axes here. We put axes just to know the components we're talking about, and then there's magnets. Some sort of magnet like this. And the screed over there. So basically, this form of this magnet that I've tried to draw there, although it's not so easy, if I would take a cross section, it would look like this. So the magnetic field has a gradient. The lines bend a bit, so there's a gradient of the magnetic field, and it's mostly in the z direction. So z direction being pointed out here. So there's a magnetic field. The beam then comes here, and the question is, what do you get on this screen? Now I have it a little too low. Beam comes there and goes through there. So the analysis that we would have to do is basically an analysis of the forces, and will be relatively, we don't care too much. The fact is that there's basically, because the magnetic field is mostly in the z direction and varies in the z direction, there will be a force basically in the z direction. Why is that? Because you take this and you say, well, that's roughly mu z bz, because it's mostly a magnetic field in the z direction, and mu is a constant, so it's basically gradient of bz. Now that's a vector, but we're saying also most of the gradient of bz is in the z direction. So it's basically dbz dz. Now there's some bending of the line, so there's a little bit of gradient in other directions, but people have gone through the analysis and they don't matter for any calculation that you do. They actually average out. So roughly, this gradient is in the z direction. I'm sorry, the gradient is supposed to be a vector. So you get a force in the z direction, and therefore, the thing that people expected was the following. You know, here comes one atom, and it has its magnetic moment. Well, they're all been boiling in this oven for a while. They're very disordered. Some have a z component of magnetic. The magnetic moment is pointing like that, so they have some components, some down. Some are here, they have no component. It's all Boltzmann distributed all over the directions. Therefore, you're going to get a smudge like this. Some ones are going to be deflected a lot because they have lots of z component of angular momentum or z magnetic moment. Others are going to be deflected little. So this was the classical expectation, and the shock was that you got actually one peak here, an empty space, and another peak there. That was called space quantization. Stern and Gerlach worked with a magnetic field that was of about 0.1 Tesla, a tenth of a Tesla. And in their experiment, the space quantization, this difference was 1/5 of a millimeter. So not that big, but it was a clear thing. It was there. So everybody was confused. They thought it was the orbital spin, angular momentum that somehow had been measured. At the end of the day, that was wrong. It couldn't have been that. People understood the Bohr atom, realized, no, there's no angular momentum there. The idea of the spin came back, and you would have to do a calculation to determine what is the value of the spin. So with the exact factor, took a while to get it right, but with the idea that mu z is equal to -2 Bohr magneton Sz over h bar, which we wrote before. Well, mu z, if you know the strength of your magnetic fields, you can calculate the deflections. You know what mu b is, so therefore you get a value for Sz over h. And the experiment suggested that Sz over h was either plus or minus 1/2. And this kind of particle that has Sz over h bar equal plus or minus 1/2 is called a spin 1/2 particle. So again, from this equation, this can be measured, and you deduce this, and you get this value. So the experiment is a little confusing. Why did this happen, and how do we think of it quantum mechanically? Now, 804 sort of began with this kind of things. And you know by now that what's happening is the following, that somehow mathematically every state is a superposition of a spin up and a spin down. So every particle that goes there has half of its brane in a spin up and half of its brane in a spin down. And then as it goes through the magnetic field, this thing splits, but each particle is in both beams still. And they just have this dual existence until there's a screen and there's detectors, so they have to decide what happens, and then either collapses in the top beam or lower beam.